Okay, I think we're ready to start. Welcome to the what amounts to the final lecture of the semester, or the final active lecture, if you will. What are we going to do? So a couple of reminders. The main reminder is that the final is on Thursday. The standard time slot for the final is 9:30 to 12:30. What do I want to tell you about the final? I want to tell you that the final will be 3 hours to do 6 problems, but you'll be given an hour to do 2 problems, and then another hour to do another 2 problems, and then another hour to do the other 2 problems, but not really an hour, more like 50 minutes with a 10-minute break between for scanning and then taking a break. So it'll be like 3 regular hour lectures altogether. The final exam will be on all the material for the entire course, from the first day of class to the stuff that we're talking about today. There's no topic that we've talked about. The usual question at this point is, what's the most important thing? And the answer is, the most important thing are the problems, are topics that we've covered in that are delineated on the review sheet and that are emphasized in the homework. And it's perfectly fair game for me to take an old exam problem from one of the previous hour exams and put it on the final exam. So you should be, that's the problem set, if you will. I recommend to you the 2 handouts, one I posted yesterday and one I just posted this morning, which have practice homeworks having to do with the topics of yesterday and today, and then 9 example problems from previous final exams. All of these with solutions, so you can study the solutions and check your own work. My strong recommendation is that you don't just start by looking at the solutions. You start by trying to do the problem and see how far you get, and then check your answers on the solutions. Tomorrow, there'll be no new material. I'll simply take the time for the active lecture to roughly divide the time into 2 parts, one of which is sort of what I think the most important things are for the course and what strategies you want to take when you're solving some particular example problems. And then the second half of the class will be basically a little like a clicker question exercise where you basically get to vote on what you think the right answers are for a number of conceptual problems, just to check your understanding. And none of that will be graded or anything like that. It'll be just an interactive exercise for fun. So that'll be tomorrow. Okay. I'm going to carry on unless anybody has any questions about if you want to check with me about, I will have office hours today. I forgot to post them already, but they'll be at 4:30. And if that doesn't work for you and you want to talk to me about any of the material, don't hesitate to send me an email and set up an appointment. But we're almost done, believe it or not. Okay. What are we going to do today? Today will be a little different. We're going to start by dealing with reference frames. Excuse me, I forgot. I need another piece of chalk here. Okay, so reference frames. And you've seen a couple of videos, these black and white videos from the 60s. They're really, I find them highly amusing. But let's see what we can say. So imagine, for example, that I have a reference frame, something like this. And that reference frame, all I mean by reference frame is an imaginary or even physical coordinate system that I would put down. So in this case, for example, I might put X in this direction, and then I could put Y in this direction and Z in this direction. It doesn't really matter what I do. And if I just put this coordinate system on the ground, then I can do kinematics. And then once I have kinematics, I can do dynamics on particles or objects. So for example, I could imagine a particle that is at some location, X and Y and Z, and that particle could be moving on a path So I could not only talk about its position, but I could talk about its velocity and its acceleration. I could do all the things I want to do once I've put that coordinate system down. And so I'll call this coordinate system O. And a different coordinate system that I could put down would be the coordinate system like this, where I have the same kinds of axes, but I'll distinguish them with a prime, so call this x prime, y prime, and z prime. And what we showed before is that, what we've kind of argued a few times now, is that if this frame is moving with some initial velocity, some constant velocity, which I'll label capital V, then any velocity of a particle, at least in the x coordinate, so if I have some particle here and it's moving and it has some motion that corresponds to the component of that velocity there would be, labeled v sub x, right? So then I could basically argue that v sub x is measured in the prime coordinate system. V sub x prime is just equal to v sub x minus v, where v is the x-word motion of this thing. So in other words, it's this basic idea that if you transform into a moving coordinate system, you have to subtract the velocity of that coordinate system. And the simplest example I tell students is just if you're on the freeway and you're driving and you're in your car, which is moving at a constant velocity v, all the other cars have speeds that are their speed minus your speed relative to your car. So for example, if their speed is greater than your speed, they're passing you, and you measure that as they go, they're moving past you. But if your speed is greater than their speed, then you pass them. They're moving backwards as you come past them. It's kind of the idea. So without going through the formal details, which are relatively straightforward, but I don't want to get tangled into them, I could do the same thing for, instead of a primed coordinate system that is moving with some constant acceleration, I could imagine just as well a double primed coordinate system where instead of moving with the constant velocity, I'm moving with a constant acceleration. So instead of, I meant to say velocity. So instead of constant velocity, now I've got constant acceleration. So because the velocity is not constant, this is non-inertial. Okay. What argument am I going to make? Well, again, without actually going into the details, if I have a particle that's accelerating with some given acceleration in any given component, let's say the ax component, then by analogy, I can argue that a sub x prime, the acceleration measured in this frame, is equal to a sub x minus capital A, the acceleration of that frame. So what so this is double prime now because I basically converted. So in other words, when I go into a moving reference frame, whether that's constant velocity or constant acceleration, the property of relevance is a property that basically just subtract, right? Basically a subtraction scheme. So we now have a mechanism for going to an accelerated reference frame from a non-accelerated reference frame. We just subtract the subtract the acceleration. Okay, well, so what? So let's keep this in our head here. Now we do the subtraction. Well, what if I want to do more than kinematics? What if I want to do dynamics? What if I want to actually start trying to apply Newton's laws? So here's the thing. The first answer to the question, what do I do when I try to do Newtonian mechanics in a non-inertial reference frame? The short answer to the question is, don't do that. Newton's laws, the first law is the law of inertia, is a law that tells you Newton's laws work properly only in inertial reference frames. If you're going to try to do physics in a non-inertial reference frame, then Newton's laws will break. So what does this mean? This means that if you have any choice at all, you should not do the problem in a non-inertial reference frame because you're going to have to break Newtonian mechanics, and we don't want to do that. In fact, we don't have to. For any problem that I will ever give you in this class, you never have to solve the problem in an inertial reference frame unless I ask you the specific question. What is the experience of being in that inertial reference frame? That non-inertial reference frame? What do you see? So again, it's not a path to solving the problem of what the forces are, but is an interesting exercise to say, what is it like to be in a non-inertial reference frame? And we're going to use the physics we know to try to infer that. So if I'm in this non-inertial reference frame, what is the story? Well, okay, so I'm going to basically write down Newton's second law. Okay, so what does that say? So this is in my inertial reference frame. So I say, okay, F, and that force on a body, which is, we'll use the vectors to make it clear what we're doing, is equal to m times a. Okay, that's cool. And so, so this is the net force, and that is equal to ma. But if I do the same exercise now for non-inertial, I put this in quotes, Newton's second law, I'm going to try to do what I was forbidden from doing, which is to try to do Newtonian mechanics in a non-inertial reference frame. Then I get F net prime equals m a prime. Well, we'll call this double prime to be consistent. That's the accelerating, that's our accelerated reference frame. You can call it prime or double prime, whatever you want. And again, this is a vector. But we already showed you that here that this is equal to the well, this is just a minus a. So I've done the subtraction now. I've converted from the acceleration is measured in the non-inertial frame to the acceleration is measured in the inertial frame. So that's just ma minus m big A. So that's the acceleration of the reference frame. With a little serif there. So this is F net, the net force as measured in the double prime frame. But we know what ma is. It's just F net as measured in the original frame. F net in the non-inertial reference frame is equal to the net force as measured in an inertial reference frame minus ma. So this is the critical equation of the whole day. Okay, what is it telling us? It's telling us that the net force as measured in a non-inertial, which is to say an accelerating reference frame, is not the same as the net force that's measured in an inertial reference frame. It's not the same. And in fact, the net force that we're measuring in this non-inertial frame is the net force that we would have measured in the inertial frame plus an extra term. This extra term. So this thing we call the real force, the real net force, right? In other words, this is basically the sum of all the actual forces like normal, weight, friction, tension, spring force, universal gravity, all of those things go here. And this thing here is what we call what's known as a fictitious force. It's fictitious because it's not actually a result of real pushes and pulls and things like that. It is simply an artifact of the reality that we're cheating by trying to do Newton's second law in an accelerating reference frame. The more you accelerate, the larger the fictitious force. So this fictitious force appears. What are the qualities of the fictitious force? So if I say, F net in a accelerating reference frame is equal to F net in an inertial reference frame plus a fictitious force, F fict, right? So what are the characteristics of the fictitious force? The fictitious force has a value which is equal to, whose magnitude is negative m, and whose direction, and times a, and whose direction is in the opposite of the direction of the acceleration. So this makes sense. Let's think about your experience. The most common experience people have of being in non-inertial reference frame is when you're in a vehicle, like a car, a train, or a plane. So if you're in a car and you're in the car, you're at the intersection, the light turns green, and you're the passenger, and your friend hits the gas, like, let's go. Okay, the car accelerates forward. You experience a fictitious force that is in the reference frame of the accelerating car that feels like you're being pushed back into the chair, right? Off you go, okay? And then your friend, who's not the best driver, comes to the next intersection, notices that the light's changing, slams on the brakes. The car is now decelerating. So that means that the acceleration is in the negative direction, that way. So that means you feel a fictitious force in the opposite direction of the deceleration, which is to say you feel flung forward. Whoa! Hopefully your seatbelt holds you on. Okay? Then your friend comes into a corner at high speed to the left, right? And you feel like there's a fictitious force that's flinging you to the outside of the car, to the right side of the car. You're basically up against the right door, hopefully not up against it, your seatbelt's holding you, but it feels like you're being flung to the right because he's accelerating centripetally to the left. Whatever the direction of acceleration, the fictitious force is opposite to it. So that's the first thing. The fictitious force is in the opposite direction of the acceleration, always in the opposite direction of acceleration. The second thing about the fictitious force that's a little weird is that the fictitious force is a mass times an acceleration. So it's almost like the MA term here. It's sort of similar. And furthermore, it's an acceleration that basically applies to the whole reference frame. Every body in that frame feels an acceleration which is both proportional, feels a force that's proportional to this quantity, which depends on the setting of the frame, and its mass. So in other words, it's a force that is very weight-like, right? Remember, the force of weight is equal to m times g, and that's, we'll basically, make this a vector by putting that negative mg j hat, right? So in other words, it's a vector that is the weight, the regular weight, real weight, is a vector force that's proportional to mass, and it points down. The fictitious force is a vector force that's proportional to mass, and it points whatever way is the opposite of the acceleration. And everybody in that frame, just like everybody on the surface of the Earth feels a weight that's proportional to its mass, everybody in a fictitious force feels a weight that's proportional to the acceleration, to its own mass. In other words, these two things are quite similar. In fact, if you ask what is your experience of any body in a fictitious frame, it's as if there was an extra weight term whose value was equal to F fixed. So in other words, so I'm going to erase this now that we've sort of come to this conclusion. In other words, the fictitious force could be thought of more as essentially as a fictitious weight, right? If I say F fixed, I could relabel that, define that as a fictitious weight, right? Whose value is equal to negative m times a. Well, that's the acceleration in the thing. And why do I do that? Well, because then I can basically define something which I call the effective weight, W effective, which is equal to the real weight, W real, that's experienced in any reference frame, plus the fictitious weight. So fictitious weight and fictitious force are the same thing. I'm just highlighting the fact that this thing looks like a real thing, right? So in this case, this is going to be basically equal to m times. So what I'm going to do is I'm going to define. I'm going to do something a little tricky here. Let me do this down here. I'm going to do a little definition just to make things kind of cute and tight. I'm going to define g, the vector g, is equal to g times j hat in a negative direction. So that's basically a little vector that points down this way for acceleration, okay? you know, and this basically is also the same thing as what I'm going to call G real, which is to say the real acceleration due to gravity. Okay, so then I can write down that the effective weight, which is m times G effective, is equal to m times G real plus m times G fictitious, right? Where G fictitious, G fict, is equal to negative A. Okay? So that means that G effective, the effective gravity vector, is just equal to the real vector plus the in the sum of the G of basically G fictitious, which is just equal to, again, I ran out of room here, so let me write this right over. I'm going to write it right over here, because it's the same thing. It's just, I'm just rewriting things in a different way. It's the same thing. So I'm going to take this, and I'm going to write down that G effective, the effective gravity, is equal to G real, which is negative m G j hat, plus G fictitious, which is negative m times A. Oh, no m. I don't want the m's. I want G. So yeah, the m's don't belong there. G effective is equal to negative G j hat, because that's how I've defined it here, minus G fictitious, which is just A. There we go. That's better. Okay. So in other words, when I'm in an accelerating reference frame, it's as if gravity has an extra term that's determined by the acceleration, the negative of the acceleration. So let's look at one kind of cute example of this. I'm going to erase, I'm going to erase this so you guys keep these things handy for just a second. So let's do an experiment. You're in a elevator. There you are. Okay, and the problem is that the elevator, basically the tension goes to 0 because the cable is cut. So the whole elevator now is falling with you in it. Okay. So you're in the elevator, somewhat unrealistically, the cable breaks. Even more unrealistically, let's assume that this is an old building and there's no safeties, there's no friction at all, and negligible air resistance to prevent the elevator from plummeting from whatever height it happens to be, 20 stories down to the ground. And you're in the elevator. That's not the best situation, but you have at least a few seconds to contemplate the nature of being in a non-inertial reference frame as you're as the elevator falls. And the question is, what's the experience? Right? So the elevator is not an inertial reference frame. The elevator is accelerating downward, right? So the acceleration of the elevator, which you're in, which is your reference frame, is basically downward. And since it's in free fall, it's falling downward with an acceleration of G, and it's going in the negative G j hat direction. So that is A. You're going down at negative G in the j hat direction. So the effective gravity, G effective, which is equal to, well, that's equal to negative G j hat minus negative G j hat. So that's equal to 0. Okay? So your experience in the elevator as you fall is that the effective weight, the effective gravity goes to 0. And the term we use to describe this, of course, is the term weightless. Okay? So if you're experiencing weightless, if you're in free fall, like you are if you're in this elevator and it's falling, you experience weightlessness. It's not because the force of gravity has stopped working. The force of gravity is inexorably pulling you down towards the disastrous assault at the ground floor. Would it be true that you could turn gravity off in this situation? You can't. But nonetheless, you experience the idea of having a sense of weightlessness. Okay, does that make sense? So being an inertial reference frame does weird and spooky things to gravity that depend on how you're accelerating. So if you're in this, so here's the thing. How do I tell the difference between real gravity and fictitious gravity? In other words, if I don't know a priori whether or not I'm in an inertial reference frame, is there some way I can nonetheless distinguish between these two physical effects, which seem to cancel each other out or at least distort each other? So to consider that, let's do an experiment. And this is a great experiment to do in a classroom because I can literally point to the doors and the windows and all these things. And I know that each of you are not here. You're located in some room, in some place, somewhere on the planet. Could be close down the street, could be other side of the world, but you're all here in some sense of the word. So just imagine, just again, a thought experiment. Imagine you're in the room that you're in. And imagine, somewhat implausibly, so if you're looking out the window, imagine, again, a thought experiment, imagine that somehow you've sealed the window so you can't see outside. And if you're in a room with doors or anything, that the doors are closed or that any openings into other rooms are sealed off. So imagine if you're in a room that does not have any access to the outside world. Furthermore, imagine that, and again, it's not true by definition because you're listening to me on the internet. Imagine that any ability for you to communicate outside that room had been cut off. Don't know why. Maybe your internet failed. Maybe something happened. You can't hear anything outside. You can't sense anything outside your room. You're in your room. Okay, so if that's not possible, that's not implausible enough. Imagine something even more dramatic happens. Imagine that for some reason, there's a highly technological civilization of space aliens with a very powerful spaceship, and they've decided that they're interested in you. And so what they do is they very sneakily arrange so that there's a harmless but effective knockout gas that is fed into the room where you are sitting right now. And as a result of that knockout gas, you're basically rendered unconscious for some period of time. And when you wake up, one of the aliens is talking to you, and the alien says to you, I hate to, welcome. I know this may be inconvenient, but what we've done is we've taken your entire room. So here's the room you're in. I'm just going to assume it's a square room for now. And we've put it in our spaceship. So there's our spaceship that the room sits in. So this is my somewhat squashed spaceship. And I'm going to represent it as a rocket ship, but it doesn't really matter what kind of ship you are. So here you are in the room. And you're in the spaceship. And what the alien tells you is that the spaceship is accelerating by some force, in this case, just a rocket, but whatever, it doesn't really matter what the force is, that the ship is accelerating towards the alien's home planet, and that you're in deep space, far away from any planets or stars, but that the ship is now moving with an acceleration in the forward direction, like this, and the magnitude of that acceleration is equal to 9.81 meters per second squared, which is to say the same as the acceleration due to weight on the Earth. So you wake up and you go, well, I don't feel like I'm in a spaceship. In fact, you say to yourself, I feel normal. I feel as if weight is pulling me down to the floor of your room. But there's no gravity. Well, and the alien reminds you, well, no, as you learned in physics 122, the effect of gravity is equal to the negative of your acceleration. So in this case, that's just equal to negative g, which is the same as the real gravity, because g, the acceleration is 9.81 meters per second. And since we're accelerating forward, the effect of gravity is basically pulling you down like this. That's why you feel as if you have weight. Making sense? So here's the question. Is there any experiment? Now, again, you're not allowed to look outside the room. You can't look out the window of the spaceship and see the stars. The question is there any experiment that you can do that would prove that this scenario, as described here, is either true or false? In other words, could you distinguish between actually being in deep space or a scenario where the alien's trying to fool you, and in fact, you're still sitting on the surface of the Earth in a building somewhere, you haven't moved at all? Is there anything you can do? And that's the question. It was an interesting question. It's the same question. Turns out it's effectively the same question that Newton was worried about in the sense of, how do you tell the difference between effects of acceleration and gravity? So if you remember, the third of Newton's worries was what we call the equivalence of inertial and gravitational mass. If I say F equals ma, the m here is inertial. In other words, it relates to the acceleration. That's that. But if I say weight, which is equal to mg, the m here is gravitational, which is to say it relates to the strength of the weight force. Okay? So Newton was worried and confused and concerned that these two values seemed to have the same value, but without any explanation. And this fundamental equivalence is the same equivalence that we're getting here between the acceleration that you feel and the acceleration that would actually really result from gravity if you were on the surface of the Earth. So how do we resolve this question? Well, it turns out that there is no resolution to this question in the context of classical physics. Nothing Newton did or anything anyone else after him for hundreds of years was able to address this kind of weird coincidence between these two different ways of looking at acceleration, one being due to gravity and one being due to actual forces. So so what happened? So who came along? So the answer is none of this was resolved until, even really dented, until the early 1900s, when Einstein came along. So now we're not going to spend a lot of time talking about Einstein in this class. And in fact, this isn't the first thing he did. He actually dealt with a bunch of other stuff first. Everything from E equals mc squared to, the theory of special relativity, where time and slows down, space gets compressed, and when you try to go fast compared to when you try to go at a speed that's comparable to the speed of light. All of these things, great stuff, great interesting things, much better to talk about in the context of electromagnetism. But for gravity, in this class, one thing we will talk about is the basis of what he called his theory of general relativity. So we've already talked a little bit about relativity anyway. We've talked about this whole business of converting from one inertial frame to another inertial frame. That's what's known as Galilean relativity. That in classical physics is any inertial reference frame is the same as any other. And what Einstein's trying to do is he's trying to extend that notion of dealing with relativity relative for inertial frames to the more general problem of basically dealing with accelerating reference frames. And in order to deal with this, he has to actually contend with the concept of gravity. In other words, he has to deal with this equivalence. So it's the basis. I can't write down, I will write down how the theory of general relativity can be represented mathematically, but we're not going to contend mathematically with the theory of general relativity. But we will, the theory of general relativity is based on a postulate, and that postulate is the principle of equivalence. So I will talk about the principle of equivalence. So what do we mean by the principle of equivalence? The principle of equivalence is that in the limit where you can't see outside the spaceship, and the spaceship is small, which is to say you can't, if you make the spaceship really big, say compared to the size of the Earth, you could measure changes in the direction of gravity from one side of the spaceship to the other. We don't consider that. Just in the case where the spaceship is relatively small and you can't see outside. So this is physics. The physicists call such constraints local, right? In other words, you only look in front of your nose. You don't look out in a way. In the case of making a local measurement, what Einstein says is there's no way to tell the difference between the scenario of being in space, there you go, thrusting away, versus the scenario of being on the planet Earth. There's no way to tell the difference between fictitious gravity and real gravity. There's no experiment that you can do. That's the postulate. That's what you start with. You simply literally can't tell the difference. And that this is built in, that gravity itself has this weird property that it is essentially the physical equivalent of an acceleration. Now, once you take that postulate into hand and you say, well, how do I do physics? How do I redo physics and make sure so that that postulate is true? It turns out that the consequences are extremely significant. All kinds of things start happening. So, for example, one classic example of what happens is, so imagine that you happen to have a laser pointer, a device that will shoot a laser beam straight across. Well, if you were actually in space and accelerating, if you fired a pulse of a laser beam, as the ship accelerates, the laser beam goes in a perfectly straight line. But the ship is accelerating, just like that video where the ball drops, but the cart is accelerating. So then the ball basically looks like it kind of is left behind. In the same way, at least in theory, if you're in space and you shoot a laser beam in the accelerating reference frame, it will look like the laser beam is being deflected down as the spaceship accelerates straight. If the beam is actually going straight, it looks to you like it's deflected. That kind of fictitious effect. Okay. So in space, if you shoot a laser beam in an accelerating a spaceship, you could see a deflection of that beam relative to a perfectly straight line, at least in principle. Now in practice, because light is so dang fast, if you ask yourself, well, what's the distance of that deflection on a distance, say across, say 100 meters, the deflection is about the size of a proton. So it's not like you're going to measure it in practice. But in principle, the light will bend. And in practice, so what does that mean? So that means that the light is bending in the presence of an accelerating reference frame, it must also bend in the presence of a gravitational field. So in other words, one consequence of this is that gravity bends light, which is really weird because normal universal gravity, Newton's gravity, light has no mass. Universal gravity depends on mass. There's no expectation that universal gravity would bend light. But Einstein's theory of general relativity, the principle of equivalence, says that gravity should bend light. And of course, you can't see that bending on the Earth because the Earth's gravity is relatively weak and the deflection is relatively small for light that's moving so quickly. But you could ask the question, what's the biggest, most strongest force of gravity that we have reasonably nearby access to? And that force of gravity in our solar system turns out to be the sun. The sun is a big thing. It's much bigger than the Earth, much more massive than the Earth. And when Einstein and his colleagues did the calculation, they realized that if the principle of equivalence is true, and gravity really does bend light, then the sun itself should bend light, at least starlight that comes close to it, should be able to be bent by a measurable amount, a few arc seconds, a few tiny fractions of a degree that could be measured on a photographic plate with a telescope. So how does that work? So here you are on the Earth, and you're looking out with your telescope in the general direction of the sun. So here's the sun over here, not to scale, not to scale. Sun, Earth, tiny. And then again, not to scale, somewhere off here is starlight. It's some stars, so there's some stars. Again, they're not to scale, these are way off somewhere. But you can imagine the light from one star that's basically taking a beam, so I'll draw the light's going in all directions from the star, but there might be one path of the beam of the starlight that comes close to the sun, and as a result, it gets deflected. This is where it would have gone, but instead it gets deflected into your telescope by the gravity of the sun. So when you look back from the telescope and you ask, what direction is that look like from? It looks like it's coming from a star that's up here instead of the star that's here. In other words, the light from the star is deflected by a measurable amount, again, a tiny amount on a plate, due to the presence of the sun. That was the prediction. That was Einstein's prediction. That this is a new way of describing how gravity worked, and that one of the consequences should be that gravity bends light. It's a crazy idea. And so astronomers started thinking, well, how can we measure this? What's the problem here? The problem is you try to look at a star where the light's coming from around the sun. The problem is that during the day, when the sun is up, the sky is blue and you can't see the stars. So eventually, astronomers solved the problem. How do they solve the problem? Anybody have any ideas? How do you solve this problem? How can you measure starlight coming around the sun when the sun makes the sky light? Anybody have any ideas? How can you turn off the sun? Is there any way to turn the sun off? Are there any events you can think of where the light from the sun no longer lights up the sky, and so you could see the stars near the sun?
Oh, an eclipse. An
eclipse, yes, exactly. So in 1914, teams of German, French, and English and American astronomers deployed to South America and Africa for a total eclipse of the sun. And they went to measure this effect, and indeed, they measured exactly the deflection that Einstein predicted. And Einstein overnight went from being basically a humble and obscure theoretical physicist to essentially a celebrity, the face of science. That's how it happened. Was this discovery? Okay, it's kind of crazy. It's kind of neat. Einstein was right. And by the way, not only was he right, as far as we know, this theory has never failed any test. As far as we know, this idea of how this equivalence is true it remains true to this day. There's no evidence whatsoever. You can always tell somebody's in trouble when they start off saying, I think Einstein was wrong. And I'll try to show you why, because they're almost never right. They've never been shown right. Einstein, at least on this theory, has never made a mistake. He's made mistakes, but not on this theory. So that's one consequence, is gravity bends light. Another consequence is that the explanation for gravity has to change. Our framework for Newtonian gravity is that gravity is a force. So Newton says that F universal gravity is equal to GMM over R squared, and negative R hat if you're going to make it a force, okay? And it turns out this is very accurate. This is very true. In fact, it's true enough, it's true to like 5 or 6 decimal places. It's certainly true enough to, basically put astronauts on the moon. That's perfectly true. But it's not perfectly, it's very accurate for many purposes, okay? But it turns out it's not true. For example, if you want to use GPS to figure out where you're located, you needed to use Einstein's general relativity to calculate the delay of the light signal coming from the radio signal coming from the GPS satellites that's due to the Earth's gravity. The gravity bends light. It also affects electromagnetic radiation in general. And if you don't take that into account, you could be mispositioned on your location on the Earth to several hundreds of meters. So general relativity is actually something you literally use every day. Every day you pick up your phone and type in, I want to go to this place, and you use the navigation. You're using general relativity, even if you don't know it. The mathematics of describing general relativity is a mathematics that basically describes space not as an absolute. Space and time are not considered essentially rectilinear Cartesian absolutes, but they're basically considered kind of like a fabric or a curved coordinate system. And if you have an object like a planet or a sun, that object basically takes that fabric of space and it bends it. Right? So the explanation for gravity is not a force. So Einstein says, no, that's not good enough. what you need is you need a mathematics that describes the fabric of space. And I can't draw a three-dimensional space. I can only draw like a two-dimensional analog that bends in the vicinity of some massive object. And as a result of that bending, a light ray that's coming along, which follows the path of space, will tend to get bent. And likewise, objects like a satellite or a planet that's around the sun will tend to get bent in their motion around that curved space. So the reason that objects look like they're experiencing a force is not because they're really experiencing force. Einstein says there is no force. It's just space itself that's bent and curved, space and time, it turns out. Spooky. So again, we're not going to do today or ever in this class the mathematical expressions. I'm not going to do math for Einstein's relativity, but for fun, I'm going to write down, it turns out you can write down the basic statement of Einstein's relativity in a simple equation, which we can unpack. So what does the equation look like? The equation looks like this. It says G, capital G, and two subscripts, which are traditionally labeled by the Greek letters mu and nu, is equal to T. Well, actually, there's a 4 pi in there. People argue about the 4 pi. There's systems where the 4 pi is there, and there's systems where, 8 pi. The people argue about it, but I'm going to put the 8 pi in there because that's what Einstein did. P mu nu plus some constant. Okay, I've forgotten something. I forgot the metric term. Hold on. Not that it matters, but I'll just leave it like that. Okay. So this term here corresponds to the effect, which is to say this is actually what gravity is. This term here, I will call this stuff, which includes matter. Okay? And this thing here is known as the cosmological constant. Cosmo constant. And Einstein realized that this term was in the equation and it could be a constant that would just be true for all of space and time. But he decided, there's no real evidence that this exists. So Einstein set this term equal to 0 for the purposes of doing his calculation. Turns out that was a mistake, but he didn't know it at the time. So even this stuff here, how are we dealing with this? This is effective gravity. So this is what you, some sense of word, experience. This is stuff. This thing actually has a name. It's called the stress energy tensor. And the reason I'm putting stuff in quotes is because, well, this includes matter, so M. But of course, there's also, as Einstein showed earlier, there's an equivalence between matter and energy. And energy, at least potential energy, is involved in gravity. So if I have matter that generates gravity, that generates an equivalence of energy, then gravity itself is in this term. In other words, gravity is in this term, but it's also in this term. Okay, so gravity, this is complicated, right? In other words, these equations are not simple. It's not just gravity equals something. It's gravity equals something that involves gravity. So in mathematical language, these are nonlinear equations. Turns out they're highly nonlinear equations. And the other problem is that this isn't just one equation. When these indexes here indicate 4 indices of both space and time. So it's basically, this is a compact form that basically connects 16 coupled nonlinear equations. This is hard math. If you take a graduate course or an upper level undergraduate course in Introduction to Relativity, you can learn this stuff, but if you actually try to apply it to solve problems, in terms of you know, it's argued that maybe there's only really a handful of people can actually really do the math to solve real new problems, challenging math. So it's obviously much more complicated than this, but you can demonstrate and you can calculate those things to some degree of precision. And people have done that for GPS and other applications. And it's different from what you get from Newton's gravity. You might ask the question, well, Mr. Koval, why don't you start with this more accurate thing? And the answer is you don't need it for most things that we would do. Even though we know Einstein's theories overthrow Newton's, Newton's is accurate to, again, high precision, 4 or 5 decimal places in most problems, certainly enough to get you to fly planes, drive cars, and even rocket to the moon. Kind of cool. So everything we've done so far has been dealing with motion. And so if you're carrying on with introductory physics, the next part is to look at what at the time, at least in the, in Newton's time, was considered kind of a weird, obscure effect, which is what we call today electromagnetism. Newton was a little puzzled about the nature of light. And it turns out there's these, magnets and little static electricity and all of this stuff that ends up being critical and fundamental as well. That's the second branch of classical mechanics, which is electromagnetism, whose underpinnings our whole society depends on. By definition, everything we do with electronics and technology is based on electromagnetism. But still, this is the first thing that people put together, was how things move. So that's it. I'm done. I'm done with the material of class. I'm happy to answer questions. There's one fun thing I didn't talk about that I sometimes mention, and I will just to finish up. It's not that relevant, but it's kind of fun. Suppose I take Einstein's theory of general relativity and I apply it to the whole universe. I guess I'm not done. I got one more little thing to do. So instead of applying gravity theory to for example, a planet or even a solar system or a galaxy, I apply it to the whole universe. So I can't draw the whole universe, but imagine I've got galaxies and stars and all of these things, clouds of dust, gas, and without going into any detail, what Newtonian gravity says that each one of these things attracts each other, right? There's a force of universal gravity between every pair. So in other words, all of these things add up. And when you turn that into Einstein's theory, that means that there's a curvature of all of space-time that's affected by all of this stuff being all over the universe. It's not a lot of stuff, and it's not a lot of curvature, but when you average it out over the whole universe, it matters. At least it should matter when you do the calculation. And in particular, what early astronomers observed in the early part of the 20th century is that if you look at large distances from here, for example, with our galaxy, our solar system, you look at large distances, the most distant galaxies, it looks like they're moving away from us. And that's kind of interesting and surprising, because why should we be at the middle of the universe? Well, we're not, but we're in a universe where the fabric of space itself is expanding. And as far as we can tell, that fabric of that expansion has been going on for 13.7 billion years. The decimal places are getting more and more accurate. And the idea is that in the past, if you run the movie backwards, all of this stuff was compressed in a single infinitesimal point, starting to the beginning of the universe, which is known as the Big Bang. So everybody knows about Big Bang theory, basically. Yeah, it's not an explosion. It's the compression of all space and time into a single point. It's not like everything was there and then that point was sitting in infinite empty space. There was no space. All the space was at that point and expands from there. And then the question is, well, what will happen in the future? Because even though the expansion is causing the universe to expand, the gravity is basically, tends to collect these things. It would cause basically things to compact. So basically, stuff in principle could reverse the expansion of the universe. If there's enough stuff, the universe will expand out and then it will come back down. In other words, it will expand out to some fixed distance, maximum distance, and then fall back down, just like a piece of chalk tossed in the air and it falls back down. On the other hand, if there's not enough stuff, it may continue. In other words, as you You know, it's like a rocket ship launching up. It keeps going up. It never comes back down. If there's not enough stuff, the expansion will just go forever, and everything will basically get more and more dilute, and that will be the end. So it turns out the amount of stuff in the universe, the matter and the energy, seems to be the dominant question about what will actually happen for the universe as a whole. Will the universe live a finite period of time and then basically come back down? So this thing I will call this is sometimes known as the big crunch, right? So you have the big bang that starts the universe and the big crunch that ends it. Everything basically goes back down. Or it may continue forever, in which case the energy will get more and more dilute, the matter will get more and more dilute, the suns will go out, the planets will decay. We'll call this the big freeze. Okay? And for decades, when I was young, we were going to answer this question, which of these two things? Now, it's kind of a cool idea. Physics can predict the ultimate fate of the physical universe. But the problem, turns out, is that all of these calculations are based on the assumption that this term lambda, which is the cosmological constant, was equal to 0. And in the very end of the 20th century, very surprising measurements seem to show that lambda was not quite 0. And the fact that lambda is not quite 0 makes all the calculations harder. So today, we're really not sure which of these two things is likely to be. It basically makes it more complicated. Most of the theories, current theories, for what lambda is, what is this thing? People don't know. They call it dark energy. It's just a name for, we don't know what that is. A lot of people working on it, a lot of ideas, some very good technical ideas. People at Case Western down the hall for me when I'm working there, always working on trying to figure out what this is. But they don't know what it is and they don't know how it's going to evolve. But most of the theories suggest that the universe will continue to expand forever. It won't crunch again. But again, Einstein's theories, you can basically start from gravity and then work your way up to the whole universe. Kind of cool. Now I'm done. All right, that's it for now. Any questions about any of that or anything else for now? So I posted a review sheet on this material. I will remind you that in terms of your studying for Thursday's exam, there'll be 6 questions. That's a 6. Of those 6 questions, at most 1 will be on the topics of, at most 1, so if it will be on the topics of gyroscope, oscillations in waves, and Einstein's gravity and non-inertial reference frames. In other words, you'll see 5 problems that have nothing to do, at least 5 problems that have nothing to do with those 3 topics. So that means everything that you've learned before this week is the most important stuff. And the stuff you've learned Monday and Tuesday, that could be on one of the 6 problems, but I consider it, sometimes the word gravy, in the sense of first study the things that come before and then study this stuff. So tomorrow morning, 10:30, we will have our, so I've posted everything I'm going to post. I'm not planning to post anything else in terms of handouts, review sheets, or problems. Tomorrow, we will have the review session, starts at 10:30. We'll go for an hour, same as usual. And then Thursday's the exam. And I've got to, I think that's everything we need to say today. So unless anybody has any questions. Otherwise, I'll see you tomorrow. And again, if you want to talk in office hours, I'll start those today at 4:30. I'll put a link up. Thanks, everybody. Talk to you tomorrow.
Thank you.